Hi everyone, my name is Thomas Homich and in the next few minutes I have the pleasure to introduce to you FargoCPT. It's a code to do 2D disk interaction simulations the easy way. The code is based on Fargo ADSG by Clément Barouteau, and a shout out to him and a thanks for letting us use his code base. In the last years it was mainly developed by Lucas Jordan and me, with contributions from colleagues in Tübingen and around the world. A few words about myself. I did my PhD in Tübingen with Willy Klei, then moved on to Heidelberg to work with Kees Doulemont to do a postdoc, which I did till this July, and now I'm a software developer. Now let's get started with the code. What does it do? FargoCPT is a grid-based hydrodynamics code coupled to an n-body code, and it is intended to simulate a 2D interaction of stars and a gaseous disk, something like this here, star in the center, a disk around. And we can also add into the mix a planet or also two. And additionally, and which is becoming more and more important, to couple the two observations, we can also simulate particles, which can be dust, but could also be something up to planetesimal size objects. Now, why should we use this code, FargoCPT, instead of maybe other codes? Well, one argument here is that we have a big package of physics modules. I think this set is unique at this moment for publicly available codes. Additionally to the hydrodynamics part and the n-body solver, we also have radiation physics. This includes treating energy transport in the disk. We have a self-correction module with current improvements by Stephen Restrepo. Believe it or not, some codes use a prescription in which the self-gravity interaction is accidentally not symmetric, so Newton's laws are not fulfilled exactly. In our case, we have a correction to this and we use the exact kernel, so we avoid using the smoothing length. We can finally select the frame of reference. So if you have your hydrogrid, your disk, you need to select around which object this is centered. Usually this is only the primary star. In our case, we can also center it around the center of mass or the secondary star, or even around planets if one wanted to do this. To be able to do the simulations, we have a special treatment of the indirect term, more to this later. We use for our n-body solver, so to treat the star and the planets, the rebound code by Hanno Rein, which is a fantastic piece of software. It's well tested, well established code. We have a particle system, like I alluded to earlier, where we can simulate hundreds of thousands of particles, and we can treat accretion onto the planets, which I think will become more important for planet evolution research. Now, a second main pillar why to use FargoCPT is the usability. It's quite easy to use actually. We have many monitoring systems, so many physical quantities you are likely to care about, like the planet positions, but also accretion rates on them, the mass of the total disk, the mass flux through the disk. All this is written to output files directly, so you don't have to worry about implementing such things. We have a test suite, so if you choose to change the code to your demands, you can run this test suite so to check you didn't change anything accidentally. We have an accompanying paper we published on the code. It not only describes the code, but it's also a nice reference for all the physics written here on the left side. And finally, something I want to mention, if you just want to give it a try and give it a quick test, go to your GitHub repository. GitHub has something called code spaces where you can launch a cloud instance of a Linux machine to try out the code in your browser. So you don't have to download anything. It sets up everything automatically for yourself and you can run this hydro code in the browser. All right, so now let's have a look at what the code actually does, get a little feeling for it. We look at the following scenario. We look about a migration scenario where we have a star in the center, a disk around it, and two embedded planets. These planets are quite heavy. So the inner planet is 9 Jupiter masses, the outer planet is 3 Jupiter masses. That carve a gap into the disk. and then they'll go about migrating. The results of this simulation look like this. The top panel is the semi-major axis of the planets, the bottom panel is the eccentricity. The semi-major axis goes from 2 to 70 AU in this plot, and you see that first the planets migrate together until they're in what's called resonance, then they migrate outward jointly, and then the outer planet does this blip, so it goes into what I call the migration jump. It goes very fast outward, stays out at this larger location for some time, and then quickly comes back in. This is a very dynamic system, for which is good that we have the rebound code included, because if you have a too simple integrator, this will screw up your simulation. Now there's already one type of output here, which you can see is the time series of the semi-major axis and the eccentricity, but there's also 2D fields, so we get full snapshots of the accretion disk. Now I'm going to show you a video of how this then looks like, and we look at the phase when the planet quickly moves outwards. The left side here is a top-down view on the disk, and you see that there's quite a lot going on, spirals in the disk. This is typical for migration, and now the planet shoots outward, and on the right you can see a zoom in onto the planet, onto the outer planet, and the circles indicate 1 hill radius and 2 hill radii. And you see that there's already going a lot on, lots of substructure here. Now, maybe in your research, your projects, you want to simulate highly dynamic planet systems, then FargoCPT would be an excellent choice. Coming back to the mass inside of the Hill sphere, so the inner circle, there's lots of mass, and in nature you would expect this to accrete onto the planet. So on the next slide, I want to talk a bit about accretion onto the planet and how this might be useful to you. First, I'm going to start with this plot here. The top plot is again the semi-major axis, the top panel. The next two panels are mass accretion onto the inner planet and the outer planet, and the bottom panel is the mass accretion rate onto the star. And here are 5 simulations shown with varying accretion efficiencies. The blue one is 0 accretion efficiency, that's the simulation you just saw, and then higher and higher accretion efficiencies. And you see that the numbers, the higher the number, the higher the accretion rate. Purple is the highest, orange is the lowest. In FargoCPT we use the Cly 1999 accretion prescription, which more or less means that we vacuum out the Hill sphere. And the parameter tells us how strong we vacuum out, so how much mass and momentum we take out from the Hill sphere. And the parameter here on the left, you see it in the legend, it's A 0.001. Well, the number is the accretion efficiency. More or less which fraction of mass do we take out from the Hill sphere every orbit. We have multiple modes implemented, so we can have sinkhole accretion where you just take everything, the more simple accretion I just explained, or also a viscous model where we assume a viscous accretion disk around the planet and then just apply a simple model to get more realistic, maybe, accretion rates. The accretion prescription can also be changed quite easily, so you just have to change some C code or C++ code. It's really nothing too big. And for your project, this might be interesting because if you run planet evolution models, for example, it could be really valuable to connect this to different structures in the disk or differently structured disks, and how the accretion rate then evolves over time to feed your models with more realistic data or more time series data. Up till now we looked at only single star systems. So we had one star, a disk around it, and planets maybe. Most stars in the universe, or in our galaxy at least, tend to be in binary systems or higher multiplicity systems. This is also something we can simulate in FargoCPT. So now I want to show you a bit about a binary star simulation done by my colleague Lucas Jordan. And here I show you a density map of a circumbinary disk and a circumsecondary disk. Well, on the left we see a zoom out, so a big disk, and in the middle there's a hole cut by the two stars. And on the right you see a zoom in onto this. And what you can see in green here is the rush lobes. The rush lobes of the primary on the left, I added here a star so you see where the primary star sits, and on the right, this is the secondary star, it's a smaller mass star. Here you see a hole. This is because this star is accreting away everything in surrounding. So that's the radius where the star accretes away everything. This is done here for numerical reasons to have no mass here. And around the secondary star, you see this nice disk. And in these simulations, the goal was actually to simulate exactly this disk. For this, if you look at the labels here, it's 0.0 and here 0.0, meaning the secondary sits in the center. To my knowledge, Lucas was the first one to be able to run such simulations because the largest star orbiting here around the secondary star causes strong fictitious forces, and usually this tends to destroy the simulation. In Fargo, we did some careful handling of these fictitious forces, also often called the indirect terms, and we're writing up a paper, or the paper is almost published now. And you can also use this machinery to run simulations of certain circumbinary planets, so planets around two stars. I think those will be discovered much more in the future. Up till now, we as a community mostly focused on planets around single stars. Speaking about observations, of course, one point of running simulations is to compare to observations, and I want to show you here one example project I did about modeling the PDS-70 dust disk. PDS-70 is a young star with an accretion disk around it, and the speciality here is that there are two giant planets embedded in this disk, and we have confirmed these planets. These are confirmed planets, and they are currently accreting. So it is more or less a poster child of planet formation. And here on the right, I show you some simulations. The left panel is the gas disk, and the right panel shows a proxy for the dust emission. And this might now look a little bit different, but that's because of the projection. On the left is the observation. We look with an angle onto the disk, so it's an ellipse. And if we actually deproject and compare the radial profiles, then you see the orange line here, that's the observations, fits nicely with the blue line underneath. This, of course, is a type of simulation you can do. Run the hydrodynamic simulations to produce synthetic observations from them. So, and then my question to you is which of the systems we know and we have data for do you want to simulate? FargoCPT will be a good choice for this. And finally, quickly summarizing, FargoCPT is a planet disk interaction code in 2D. It has a multi-physics package with radiation, hydrodynamics, and self-gravity. Many of these things are not non-trivial to implement. So if you want to implement this physics or check out how it works, look at the code paper. It's a great reference, I think. And finally, FargoCPT is quite easy to use compared to other codes. I highly encourage you to check out the GitHub repo, launch the code spaces, and just give it a try. With this, I want to thank you for your attention, and if you have any questions about the code, how to run it, how something works, feel free to open an issue on GitHub or just write me an email. Thank you.